Hello, my name is Taran, and today I'll be presenting Lab 3 Magnetic Field of a Bar Magnet. The problem we're trying to solve today is to determine the magnetic dipole moment mu of the magnet as well as the field along the 45-degree axis. Theoretically, if we know the force of the magnetic field, we can calculate the magnetic dipole moment and then calculate the magnetic field along the 45-degree axis. This is made possible by our two equations, the magnetic field along an axis, which allows us to calculate the magnetic dipole moment and allows us to make these predictions. In doing this experiment, we have a few assumptions. First of all, we assume the magnet has a constant magnetic field. We assume the Earth is treated as a bar magnet. We assume all objects are stationary when the measurements are taken. And we assume that there are no other forces causing magnetic fields other than the magnet and the Earth. In our experimental setup, we have a bar magnet, 2 meter strips, a smartphone with a magnetometer app, and tape. After setting up the experiment shown in the lab document and the picture, we record the measurements at various points in the spreadsheet. We then use the equations to calculate the magnetic dipole moment and the n for the equation. Here are the measurements that I took and the graph is shown. As you can see, our equation for the slope is y equals negative 3.1416x minus 14.312. In this equation, our n is negative 3.1416 and our k is negative 14.312. Here's the glow strip code. I've attached all the information that I changed. As you can see, the mu, the magnetic dipole moment, is 3.04. I've defined my dipole B function. My B scale was 1 times e to the 4th. My distance was 0.3. You can see I made my vectors for the distance, negative distance, and following. We have our axes set. And at the end, we have our arrows for our observation locations. Continuing, here are more arrows. Our D perpendicular is 0.212. Our 45-degree axis is almost 45 degrees. Here's a recording of the glow script. General observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. The small x component is present as a result of the Earth's magnetic field. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The opposite is also true. As the magnetometer moves farther away from the magnet, the measured x component decreases. What if we didn't orient the experiment to compensate for magnetic north? If we had laid out our meter stick at some intermediate angle with respect to the Earth's magnetic field, our results would change. Our x and y magnetic measurements would be affected by the x and y components of Earth's magnetic field. This, in turn, would lead to inconsistent measurements and cause students to have non-uniform results. Overall, we would have skewed results that would be hard to compensate for. What if we were to stick two identical magnets together end to end and run the experiment again? The force of our experiment would change. Once again, we would have different x and y magnitudes. As a result of the two magnets together, we would have double the magnetic moment as a single magnet. We could then treat these two magnets together as a single magnet with double the magnetic moment. Our forces overall would be greater, and our magnitudes in the x and y directions would be greater as a result of the greater field produced. Error sources and how to improve. Other magnetic objects around could have caused imperfections in our measurements. These include objects like desks, pens, phones, and watches. We can mitigate this by taking measurements as far away from objects as possible, which is something I tried to do in the experiment. A second error source is that the phone sensor is not completely accurate. It's not professional grade equipment and is a cheap sensor in a phone. This can be fixed with professional grade equipment. And the third error source is measurements are not perfect. They're as good as can be with human eye and tools that will lead to slight imperfections in calculations, but we still have to account for these. In conclusion, we became familiar with the magnetic fields of bar magnets and the Earth. We were able to calculate the magnetic dipole moment of the magnet mu. In this case, it was 3.04. Our n was negative 3.1416. We were able to do this as a result of the equations for a magnetic field shown below. Using these equations and our calculations, we can form accurate models for magnetic fields. Thank you.